So the next topic is quotient theorem. Quotient theorem or quotient law. Quotient theorem or quotient law. What does it say? It states that if AA is a vector, here it is a contravariant vector, it's a vector, and this AA, B, ABC. This is equal to Q subscript BC is a tensor. Then P ABC is a tensor. So I have a vector AA, I have a vector later. Adudagi AA high visiga P ABC high object siga and easy multiply tore. Adudagi A gi superscript siga A gi index siga P gi hanwe index A siga and easy manahale summation tore. So the amana upper index A, amana lower index A. Upper index amaga lower index amaga manaragadi ayang asai high kiba summation is implied. That is called the Einstein summation convention. So sigi A high object sigi index siga P high object sigi lower index siga manahale summation tore. Tara eva answer tara eva quantity do that quantity Q BC should tensor whatever. So in this expression A should tensor whatever, Q should tensor whatever. Otherwise P high should tensor organi high. Magi meaning the A should tensor whatever, Q should tensor whatever. Aduga tara eva sigi adoragadi sigi P ABC sisu. This will also be a tensor. Adugi meaning ni adudagi matanga. Let us consider some operations with tensor. Tensor operations. Number one, the addition. Addition hana see addition is kind of adding corresponding components of two tensors of the same type results in quantities that are the components of a tensor of that type. Say for example, in the operations with tensors. Operations with tensors. Number one, the addition. So the A have A have a tensor see its type 1, 2. This is a tensor of type 1, 2. Matakta makha index ani. This is a tensor of type 1, 2. Siziga same type oiba. Atopa tensor amagamu tinsanaraba. Already I'll get a new tensor which is also of the same type. That is 1, 2. Siniko magi meaning ja. Aduna adding corresponding components of two tensors of the same type results in quantities that are components of a tensor of that same type. This is addition. Addition kangadi multiplication imply to next the multiplication. Multiplication later. Multiplication is makal ani later. Multiplication kanana multiply multiplication by a scalar or multiplication by another tensor. So first let us consider multiplication by a scalar. Multiplication by a scalar. Suppose I have a tensor of type say PQ type tensor later. I would tensors data in a scalar field phi multiply tore. I have a tensor of type PQ and I multiply it by some scalar phi. And I will get a new tensor, even new tensor though, it will be of the same type PQ. PQ. Say examples data A B C D sigi to type 1 3 tensor am laureba sigi tensors da aina scalar field phi sina puri saleba adorgadi I'll get a new tensor B adu magi type ti hanagi tensor type siga chamana ganeba B A B C aduna scalar amana tensor amada multiplication to matamda tensor du type to change the word multiplication by another tensor. Multiplication by another tensor. Tensor multiplication. Tensor multiplication. Tensor multiplication. Tensor multiplication. I have a tensor of type P1 Q1 type label tensor amaga P2 Q2 label type of tensor amaga. So I am multiplying a tensor of type P1 Q1 with another tensor of type P2 Q2. This will give rise to a new tensor of type P1 plus P2, comma Q1 plus Q2. So example D, I have a covariant tensor of type 0, 1. This is type 0, 1. Then I have another tensor of type 1, 1. So this will give rise to a new tensor of type 1, 0 plus 1 d 1, 1 plus 1 d 2. So this is of type 1. This is tensor multiplication. Another tensor of operation, the contraction. Contraction. Contractions in a carino. Contraction this operation amounts to setting a subscript equal to a superscript and summing over. I repeat, this operation amounts to setting a subscript equal to a superscript and summing over. Say for example, I want the x tensor and it is of type 1 3 I have a tensor x of type 1 3. So you see x is A B C D type 1 3 never. So A is a B is a contractor or contraction on A and B. A and B. A will be contractor or the A will be manahalaga summation to high. So that means x A C D. So A is contraction to record. A contraction to record. I have a postal. So I have a tensor of type 1 3. So there is the A hariba mathaki upper index siga B hariba makhagi lower index siga aniji manahalaga contraction tawre, that is XAACD. This will give rise to a new tensor of type 02 CD. A is a contraction tawre, so this will be a new tensor of type 02. So 1 lerembadu amahandarani 0 dandarani 3 lerembadu amahandarani 2 dandarani. So contraction tawradi 1 3 lerembadu 0 2 dandarani. This is called contraction of tensors. Adudaki akoina another tensor akoina yam twin thengnabadi Kronecker 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 tensor. This is the tensor delta AB. Tensors in Evoca. If A and B are equal, this is equal to 1. If A and B are not equal, this is equal to 0. I repeat, if A and B are equal, this is equal to 1. If A and B are not equal, this is equal to 0. Madi, in whatever coordinate system you choose, it always have this same component. Chronicle tensor GD, whatever coordinate system it is used, its components are the same, which is so it is represented by delta AB. This is the Chronicle tensor. Chronicle tensor je koina yam toina siznarkaneba. Next koina hojik amu
sir hojikkido amuka hanbiyo chronicle tensor gido.
Next amu symmetric and antisymmetric tensor. Symmetric tensor hana khana zero. Symmetric tensor hogi hierarchy A subscript A B siga A subscript B A siga manarabo. Sigi index and is when I interchange these two index. Aduna A subscript AB is equal to A subscript BA manaragadi. This tensor is called a symmetric tensor. So this is a symmetric tensor of type 02. So I talk to symmetric tensor of type 20 A AB is equal to A BA. So this is a symmetric tensor of type 02. This is a symmetric tensor of type 20. Already symmetric tensor how many independent components will be there? If we are talking about n number of dimensions, n dimensions this A, small a can take values from 1 to n. This B can also take values from 1 to n. So the n times n square number of components n square number of components but not all the components are independent. Independent a tensor of rank 02, a tensor of rank 02 or 20, sorry, rank type, a tensor of type 02 or 20 or 11, a tensor of type 11. Rank 2 tensor 0 go 2 go stationary 2 tare, so 2 go 0 go stationary 2 tare, so 1 go 1 go stationary 2 tare. Rank 02, rank 20, rank 11, sigumbo tensor sorry, type 02, type 20, type 11, these are tensors of rank 2. Tensors of rank 2 they can be represented by matrices. Tensor of rank 2 matrices that represent the way these are like the components of a matrix. Matrix key elements these are like the elements of a matrix. Elements we can view this like the elements of a matrix. So n by n square matrix magi elements kam lagini n square number of elements lagini. But if the matrix is symmetric, how many independent elements are there? N dimensions, the number of independent elements are n into n plus 1. Sorry, this is capital N. So let me write it as capital N. N into n plus 1 by 2 independent elements like an independent elements. So in n dimensions, a symmetric matrix has n into n plus 1 by 2 independent elements like an So I talk the antisymmetric. Antisymmetric or skew symmetric. Antisymmetric or skew symmetric metric. Tensor. Antisymmetric or skew symmetric tensor hierarchy. Matrix ke domaina A subscript AB is equal to minus A subscript BA. I index and is interchange the minus sign and color. These are the elements of a skew symmetric matrix. These are the elements or these are the components of a skew symmetric tensor. These are the components of a skew symmetric tensor. The matrix on matrix on antisymmetric matrix the n dimensions the antisymmetric matrix ki independent elements kya lay n dimensions the how many independent elements are there? There are actually n into n minus 1 by 2 independent elements. Independent elements. There we go. Another notation. A notation which is frequently used to denote the symmetric part of a tensor. Aduna kaino haigadi x have a tensor x have tensor is the first bracket the AB iraba AB x have first bracket the AB iradi. This means it represents the symmetric part of this tensor. That is, it is equal to XAB plus XBA. XAB ga XBA ga tijanardi matam chapter symmetric dum tarani pa. Aduna matrix amagi sorry tensor amagi magi symmetric part to e ga x harga subscripta within first bracket AB. Antisymmetric part to e ga na, so this is the symmetric part. Antisymmetric part e ga na x third bracket AB. This means 1 by 2 x AB minus x BA. So this is the antisymmetric part. Antisymmetric part. And tensor amagi symmetric part, antisymmetric part se first bracket ka third bracket ka jina so EPI notation we can associate tensors of different types. We can associate tensors of different types by contraction with the covariant metric tensor or the related contravariant metric tensor. Metric tensors we can also associate tensors of different types. Aduna, we assume that the manifold has a metric tensor field with components. Manifold MJ. We assume that this manifold has a metric tensor field GAB. I repeat, we assume that the manifold has a metric tensor field with components GAB. And GAB have a tensor now. GAB is a symmetric tensor. GAB is equal to GBA. This is symmetric tensor ni adudagi maje non-singular oi. Non-singular oi have the GABC matrix on iraba. In some coordinate system, this GAB can be written as a matrix. Adugadi coordinate system da sigi inverse levels. Matrix sigi inverse. Sigi matrix sigi inverse. Adugadi GAB exists over. Non-singular have the metric is non-singular means the inverse of the matrix exists. And a matrix square matrix this is the metric tensor, and this is the metric tensor written in matrix form. Aduna metric tensor is matrix form the iragadi magi inverse to exist whenever. That is the meaning of the term. The metric tensor is non-singular. Then, how are these two elements? How are the elements of these two matrices related? These elements, they satisfy this relation. G A B G B C is equal to delta. So B summation to summation over all possible values of B. A GAB GBC. Sigi matrix siga ani je amana amagi inverse ni habigidi magi elements do sigi conditions satisfy to bane ko adulagi amuk GAB habasi symmetric tensor ore banina aina sigi tensor ji matrix form the iradi. The matrix will also be a symmetric matrix. Symmetric matrix ore banina symmetric matrix amagi inverse to symmetric matrix adum oigane. So that means G superscript AB is equal to GBA. So I say metric tensor ki khangre. This is a tensor of type 02. Now this is a tensor of type 20. Mass is symmetric oire banina massu symmetric oigane. And we can use the quotient theorem to prove that this GAB, these are the components of a tensor of type 20. The metric tensor with components GAB, this can also be used to lower suffixes. And this metric tensor with components capital GAB, this can be used to raise suffixes. For example, in one the A, B, D, C have. Suppose I have a tensor of this type. This is a tensor of type 1, 2. Sig tensor of type 1, 2. So that if I multiply by this contravariant metric tensor, A, D is multiply tawre. A, D is multiply tawre. D is repeated oibanina. This is sum over tawre. I will get a new D is sum over tawre ni A, B, C. I'll get this. Aduna index sigi contravariant metric tensors na raised over. Aduna index raised over. Index can be raised by this. Aduragi amuk sidala sigi A j not sigi B j, I can also lower this B. So suppose A, B, C has. If I multiply this by G, B, D, the DB has. So you B, Z, this B and this B, they are the same. So was a contractor on honey, this B will be lowered. A, D, C. So you B just to put it by multiplying by this metric tensor. Covariant metric tensor, so no contravariant metric tensor coordinate. So this is covariant metric tensor and a covariant, so this is a contravariant metric tensor and a covariant. Record. The swine to the tensors. So sigi tensor ziga manabra anagadi. These two are not the same, but these two tensors are said to be associated. These two tensors are said to be associated tensors. Associated tensors which may be obtained from each other by raising or lowering indices are said to be associated tensors. And we use the same kernel letter sigi a adum sine capital A adum sine ko by convention sigi adum capital A adum sine, but these two tensors they are not the same, they are said to be associated tensor. Yare ko adudagidi akoina tensor da another source of ambiguity is kaino haibakanda more than one tensor of the same type may be associated with a given tensor. For example, a tensor ambiguity ko AB have a tensor this is a tensor of type 20 nika. This is a tensor of type 20. So if I lower the first index, I fangani AB have fangani. So this is a tensor of type 11. Since I can also lower the second index. First index thamaga, second index on a lower to. So I can also lower the second index AB. So this is also of type 1,1. But sigi tensor anise mana brava. I'm on a first index lower to one, I'm on a second index lower to one. Manabra, these two are not equal. These two tensors, they are not equal. Aduna aikoina tensor gi index lower to bakanda magi ngasai first index lower to rogana magi mapadura thambiroba. Second index lower to rogana b gi mapadura thambiroba. So the ordering is also important. Aduna sigi indexing je careful spacing to but if these are symmetric matrices or symmetric matrices or but symmetric matrices or so let me stop the recording here.